Hello, welcome to A-level physics and mathematics class. In this episode, we are going to break down Kepler laws of planetary motion. So Kepler published his a book saying that like Astronomia Nova published in this book. He mentioned that two of his laws, which is Kepler first law as well as Kepler second law. So, like I said, Kepler published his book on 1609, and then he mentioned in that Kepler first law as well as Kepler second law in Astronomia Nova. Okay, now that is what we are going to break down in this episode. So, before that, could you please like, share, and then subscribe to this video? That will help me a lot. Thanks so much. So let's proceed with his laws basically. So his first laws is basically, we call it a law of ellipse. Okay, we call it a law of ellipse, which is his first law. Okay, this law is stated that the planet move in elliptical orbit. Okay, in a elliptical orbit with the sun is located one of the foci. Okay, let's say this is an ellipse. Okay, this is a kind of ellipse which is stretched circle, not exact circle. Basically, its orbit is not a circle. Okay, you need to understand it's a kind of elliptic. I mean, it's a kind of stretched circle. Okay, so that is called a ellipse. Okay, so his first law is stated that the planet is moving, or the planet is moving in elliptical orbits in which the sun is located in one foci. So let's say this is a two foci. Basically, foci means a plural form of focus. Okay, this is a focus, and then if you have a one focus, you can say that a focus. Okay, foci is a kind of a plural form of focus. So this is a foci. So the sun is located one of maybe in this foci, or in this focus, or in this focus. Okay, I took this focus for you just for instance. So the sun is located in this foci, and then the planet move along the orbit, or along the planet is moving in this orbit, which is called, like I said, a laws of ellipse. Okay, laws of ellipse. That is what we call it. So that is what we call it. First law of, or Kepler first law. So like just to summarize, the planet is moving, or the planet is rotate in elliptical orbits when the sun is located in one foci. Okay, so that is it, and just let's see the piece of, or the key piece of ellipse. So this is a major axis. As you can see, this is a kind of major axis, which is a longest diameter of the ellipse, and then this is a minor axis, and then this is a minor axis, which is basically a shortest diameter of the ellipse, and then this guy is a semi major axis, is a distance between one edge of the ellipse to the center of ellipse. Okay, this is a semi-minor axis, which is basically distance from the center of the ellipse to the edge of ellipse. That is just a piece of key terms that you need to know in ellipse. Okay, so let's proceed with the second law. Second law is basically stated that a line connecting a planet, or the line connecting a planet to the sun is sweep equal area in equal interval of time. Okay, so the line, like as you can see, this is the line connecting the sun. Okay, the line connecting a planet. Okay, the line connecting a planet to the sun is with equal area in equal interval of time. Okay, that is what we call it, the law of equal area. Okay, that is what we call it, like I said, the second law, or law of equal area. So meaning that, let's say this is an ellipse, and then we have a kind of planet over here, and then as you can see, this planet is moving like from this, or I took basically the major axis of you can take any axis as well, you can draw any different axis, but what I'm trying to say is the area basically this area, let's say this area 1 and then this area 2 is exactly the same. Okay, that is what we call it, law of equal area, or the Kepler second law. Okay, that is about Kepler second law, meaning that basically that means the planet move faster, faster than, like, let's say that the planet is moved faster when the closer to the sun, meaning that in this area or in this region, the planet is moving faster when it's closer to the sun, as well as the planet is moving very slow when it is far from the sun. Okay, that is what we call, that is basically it's about the Kepler second law, or law of equal area. Okay, that is it. At this point, basically the sun, the planet. Okay, the planet moving, or move, you can say moves faster. Okay, faster, and then in this region, the planet moves slow. Okay, you can say slow or slow. So that is about a second law of, or Kepler second law, or we call it law of area. Okay, that is it for the second law. And then Kepler, he published another book saying that harmonious world, which is basically a third law. In this book, he published the third law. After 10 years, he published the book, says that harmonious law. And then this laws is that stated that the square of the planet, or the square of the planet's orbits. The orbital period. Okay, basically, it's the square of orbital period is directly proportional to the semi-major axis. Okay, the square of the orbital period, which is basically we can represent with T or P, and it doesn't matter, you can use a T. I use a T over here. The square of a orbital period is directly proportional to the semi-major axis. Okay, that is what we call it a Kepler second law, Kepler third law, or we call it law of period, or harmonious law, or law of harmonious. Okay, because like I said, Kepler, he published this law in his after 10 years in his harmonious world book. Okay, that is why we call it the law of harmonious. Okay, so that is it for this episode. Basically, I just want to let you know this is this is a direct relationship between the orbital period as well as the semi-major axis. As you can see, this is a semi-major axis. So this is a direct relationship, meaning that the orbital period is the square of orbital period is equal to with the cube of the semi-major axis, and then you can find out the orbital period is equal, we can find basically with this formula, which is the orbital period square is equal to with the semi-major, or the cube of semi-major axis. So let's say we have as you know that I'm not so sure if you are familiar or not, the the astronomical unit of Earth is equal to 1, and then Mars is a bit far from the sun, and then the astronomical unit of the Mars is equal to 1.25, and then to find out the time period, okay, the orbital time period, you can use this equation or this formula, so which is basically T square is equal to, we can plug this guy over here to 5 for astronomical unit. Okay, this is astronomical unit cube, so you will get basically you will get 1.88 Earth year. Okay, we call it an Earth year. Okay, that is what you can get, Earth year. Okay. So that is basically just a quick example, and then that is what I was trying to explain for you guys. So let me know if you have any question in this regarding with Kepler first, second, and third law. So yeah, that's all for today, and then see you in next episode. Before that, like I said, could you please uh, like, share, and then subscribe this channel? That will help me a lot. Yeah. See you in next episode. Have a good day. Thank you. Goodbye.